Brandon, and I'd like to talk about my master's research named a preliminary comparison of Dithiothreitol against Tetrakis hydroxymethyl phosphonium chloride in N-Isopropylacrylamide polymer gel dosimeters. It's a lengthy title, I know, but I'll explain it as we go through the presentation. Before going, I'd like to thank my supervisors, Pejman and David, for letting me do this project. So here's a brief overview of what I'm going to talk about. I also would like to thank Fiona Stanley, Charlie's, and Royal Perth for letting me for the collaboration and letting me do this project as well. So polymer gel dosimeters are 3D relative dosimeters. So in radiotherapy at the moment, what we have is that we have ion chambers that measure dose or point doses. We have film dosimeters that measure dose in 2 dimensions, but we haven't yet implemented gel dosimetry or polymer gel dosimeters, which measure dose in 3 dimensions. The way that polymer gels work is through a process called polymerisation. So say if we've got components A and B, which are called monomers, we expose them to photons, high energy photons or electrons, and then they then combine together to perform chemical stability. And this is what's called a polymer. And the monomer that I'll be using in my project is called N-Isopropylacrylamide, or NIPAM for short. So the gel is comprised of 5 main constituents. So it's mainly made of water, which is around 89 to 90%. And then it's mixed with gelatin, which is around 5%. We have a crosslinker. So what a crosslinker does is that if we have 2 polymer chains and we want them to link together so they can precipitate out of the solution so we can see what's happening, that's what a crosslinker is. And the crosslinker that I'll be using is called methylene bisacrylamide, and which I'm just going to call it bis for short, and that's what's called in the literature. The monomer I'm going to use, as mentioned before, so NIPAM, and then after adding all of those together, we can add something called an antioxidant, and that eliminates any oxygen contamination or tries to sweep up all the oxygen from the polymer gel. And so when we have a polymer gel dosimeter, we can a really good application of this is that we can use it for patient-specific phantoms or phantoms that have different shapes or sizes that are not cylindrical or not as simple like a sphere or rectangle, like a head. And then we can verify its dose using treatment planning systems. So antioxidants, well, the role of the antioxidant in gel dosimeters is to reduce the impact of oxygen. And so oxygen acts as an inhibitor in polymer gels, and so it stops the gel from performing at its absolute best. The main antioxidants that are used in polymer gel dosimetry is Tetrakis hydroxymethyl phosphonium chloride, or THPC for short. So even though it is quite well known in the literature, it is quite toxic, and so you have to handle it with care. It is toxic enough that you can't even put it down the sink because it is quite a danger to aquatic life. Another antioxidant that is worth looking at is Dithiothreitol, or DDT for short, and is a sulfur type of antioxidant. It's not so well known in the gel dosimetry literature, but it has the main advantage of not being as toxic compared to, say, the THPC. And so my main research aim is to observe if DDT is a suitable, less toxic antioxidant to the NIPAM polymer gel dosimeters. So I did a literature review which assessed all different types of antioxidants that have been researched. You can see that with THPC is quite prevalent as it tested with different types of monomers. And then below that, we've got ascorbic acid or vitamin C with copper sulfate. And the way that works is that the oxygen gets so swept up as in the metal complex. We've got other antioxidants like hydroquinone, DDT, green tea, and N-acetylcysteine. What I'll be focusing on is these 2 right here. So we've got the NIPAM monomer with the THPC antioxidant in MRI, and I'll be also looking at DDT with methyacrylic acid, which is what MAA stands for, also using MRI. So I wanted to, in this project, wanted to add more information on how NIPAM gels react with DDT, or how they behave under DDT antioxidant. And so since this is an experimental project, this is the summary of the layover. So we've got its construction, making of the polymer gels. We're then going to irradiate them, then image them using MRIs, and then we're going to do some image processing analysis. So so the gels were made, so two types of gels were made under normoxic conditions, THPC with 10 millimolar and DDT with 10 millimoles per kilogram. Normoxic means that it was just made under normal atmospheric temperatures and pressures. And since I've been making lots of iterations, as in making lots of gel, I just automate the whole process in Python 3, so it spits out a recipe. So this is the main, you can say, workflow of how to make the gels. So initially add some water and then add some gelatin, let it swell for about 10 minutes. You then heat it up, add the cross-linker, and then cool it down, add the monomer, and then you add your antioxidants, so it could be THPC or DDT. And then what I did is that I poured it into phantoms and then calibration syringes before putting in the fridge for more than 24 hours. So I made 7 calibration syringes and I used an 800 ml rectangular phantom. And this method was actually based on Sendin and et al. And Khan. So Sendin did the NIPAM THPC recipe, but Khan did the DDT, but with, instead of the NIPAM monomer which I'm using, he used a methyacrylic acid. And so after making the gels to be in the fridge for more than 24 hours, I need to calibrate the syringes. So with the calibration method, I use the water tank. I use 6 megavoltage photons. They're radiated at 1.5 centimeter depth dose, which is usually where that is. Is usually the maximum depth dose. When in water, I use a 10 by 10 centimeter field, 100 centimeter source to center distance, and 7 syringes. So if you look at the schematic on the top right-hand corner, initially measurements were done using an ion chamber to correlate the amount of monitor units with the amount of dose received. And the reason why we use 10 centimeters of water is so that we eliminate any electron contamination that might add to the readings. And then after we get the correlation between the amount of monitoring units and the dose received, we then used our setup for calibration syringes. So you can see on the bottom left-hand corner, we've got the ion chamber situated in the middle, and then on the right, we've got the calibration syringes. That piece in the middle is 3D printed, and so it was hot glued onto the water tank, just so that like the syringes have somewhere to sit. So after calibrating the syringes, we then irradiated the phantoms. And so we used 100 centimeter source to surface distance. We used 6 megavoltage photons. We used a small 3x3 field so that it fits inside the phantom. And we tried to deliver 8 gray at the maximum depth dose, just so that we can clearly see that it's been irradiated. So if you see the pictures on the top left, we can see that we use the light field as well as other methods to make sure that it's 100 centimeters source to surface distance. We use the spirit level to make sure everything is balanced and even, and then you can see the light field on the bottom. To image them, we use MRI imaging. So at Finis Stanley Hospital, we use a Siemens ERA, and at so Charles Gardner, we use a Siemens SCARA. We place the gel dosimeters in a head coil and we use T2 weighted imaging. So that usually means you have a short echo times, so short sample times over a long repetition time. And these recommendations were put forward by Dedeen and others in around 2004. You can see in the image that inside the head coil, we see that the polymer gel, so the syringe, the calibration syringe is surrounded the polymer gel, and that bit, that blue bit, is actually 3D printed. So it's so that we can measure the phantom and measure the calibration syringes at the same time, just to save time, because these MRIs are clinical MRIs, so not research MRIs. So there's a lot of time pressure with patients and whatnot. And so when I'm analyzing the results, what I'm mainly analyzing, the main unit that I'm analyzing the MR images is called T2 time. So spin-spin relaxation. So T2 is the decay of the transverse magnetization caused by the proton exchange energy with other neighboring protons through the interaction of local magnetic fields. And it's given by this equation here. So it decays exponentially. And the time it echoes just means snapshots and receiving a signal. So for the same slice, as you can see on the GIF or GIF on the top right-hand corner, you can see that over time through the different echoes, it starts to get a little bit darker and darker as the transverse magnetization decays. And so how I get a T2 mapping or T2 image is, I'll walk you through it. So say if we've got a red voxel on that's in the image on the top right-hand side, I plot the magnetization over time and over a chosen slice. I then fit it to an exponential curve, and then we get the T2 time, which is 1 over negative b. So b is just the constant on a constant exponent of the exponential, and then we map it to an image. So we do that to every pixel, and then we can get ourselves a T2 map. For the results, so initially the normoxic DDT gels polymerized before radiation. You got this pebble that sort of formed. So we tried to characterize it using NMR, but the problem was that it didn't dissolve in any of the solvents. So we couldn't use it. So NMR is basically the gold standard of trying to characterize any sort of chemical, as you can sort of deduce its chemical structure. We tried using IR spectroscopy, but there weren't any meaningful results from local libraries. So you can see the scan on the bottom left-hand side with transmission on the left and wave number on the right. So ideally what you should to have for reliable results is a transmission of over around 50%, which is best practice. But we don't really have that. And the local library suggested on, as you can see on the right-hand side, which is hydroxypropyl methyacrylamide. The difference between the scan on the left, which is my results, and the scan on the right, is that it's sort of missing a sort of a peak at around 1,300, which is the NH stretch. So that wasn't really present, even though it's present in the monomers and the crosslinkers that I've used. So it didn't really produce any meaningful results. And the problem with IR is that you can't use it by itself. It's sort of used as like a confirmation tool to confirm the functional groups that you have, but you can't really use it by itself to deduce its structure or its chemical pickup. So being curious as to what why the pebble formed, I wanted to see what happens if I reacted the DDT with just the individual components. So I had the monomer, gel, and cross-linking gelatin, as you can see in table 1, but there was no reaction with any of them. And then since that didn't occur, I wanted to see whether it's the two of them. So I tried the monomer and the gelatin, the cross-linking gelatin, but turns out that if you put the cross-link and the gelatin together, you get a white pebble that's formed. So, okay, that's interesting. We can't just take the cross-linker out of the polymer gels because you won't precipitate, you won't see the polymerization that's formed. You need something to precipitate out and make sure it stays where it is. So we think, is oxygen also a factor? So I did a test of 3 polymer gels, NIPAM anoxic, DDT anoxic, and THPC normoxic. The way I achieve anoxic conditions is just bubbling it with copious amounts of nitrogen, which is adapted by Spavek et al. So I bubbled it 30 minutes before adding the antioxidant and 20 minutes after adding the antioxidant. And so Anoxic means that it's just it's sort of eliminated with oxygen, but not made in an oxygen-free environment. That's called hypoxic. So as you can see, the nitrogen is coming in through the orange tube and then bubbling out through the clear tube. So when I measured these the syringes, all the calibration syringes failed. So for the DDT anoxic, it polymerized before radiation, and you can see on the graph on the right-hand side with relaxation time on the left, on the y-axis, and dose on the horizontal axis. What should happen is that you should see a linear upward trend, but what we see is sort of like this general mess of going down and then sort of scattering itself back up. So that's the anoxic one, but for the THC normoxic, it did sort of have that linear upward trend, but the sensitivity, which is defined by the gradient between the relaxation time and the dose, would underperform what's happened in the literature. So what I measured between 0 and 10 gray was 0.028 per second per gray, but Chen and others measured something a lot higher. And also for the NIPAM anoxic, there was no response. So as you can see, it is a bit of a mess right there. And the main reason was that for both the DDT anoxic and THPC normoxic, it polymerized before radiation, so they were effectively spoiled. And for the anoxic, there was no response. For the phantoms, 2 out of the 3 phantoms did not show any irradiation. For the DDT anoxic one, we found some irradiation, which is really, really good. So you can see the small field irradiation that's characterized as white, with the calibration gels on the right-hand side. So you can see it from 0 and 10 gray, there's not much difference between them. So that must have meant that it polymerized before being irradiated. And then you can see the T2 mapping also on the right-hand side with the arrow pointing where the beam entered in. So for the normoxic one, all of it polymerized before the phantom polymerized before being irradiated. So it was effectively spoiled. And when I looked at the T2 time, there was no response. And same for the NIPAM anoxic, where it didn't even do anything at all. What was interesting is just that I thought maybe temperature might be a factor in the pre-polymerization. So I did some tests to see with gels being set at room temperature and gels being set in the fridge. And this was using the DDT anoxic gels. And as you can see on the image on the right-hand side, your the one on the room temperature polymerized and looks quite cloudy. Well, on the left-hand side was the one that's been set in the fridge, and it still remained clear except for a small band. So at room temperature, the gels polymerized faster than those on the left. And also the time-lapse study, where I just sort of made the gel dosimeter and just left it there on the table to see what would happen. And then over time, you can see the dark magnetic stirrer just disappear behind the white precipitate that's formed. And I also think that it might be the gels that I've made before polymerized because it was too slow to transfer into the fridge. I should have immediately placed in ice water bath. And so we think I think the oxygen and temperature were a factor. And when I say oxygen, I think the lids weren't sealed properly because the spring was taken out of the MRI scans. And so just using the DDT anoxic phantom, we could still get a lot of information out of it. So what I measured first was the penumbra. So the penumbra is just a difference of the distance between 80% and the 20% dose. And so at for the ion chamber at a depth of 15 millimeters in, this had a This had a penumbra of 2.7 millimeters, but for the gel dosimeter, it was 2.81 plus or minus 0.47 millimeters. So the gel dosimeter was within uncertainty of the ion chamber measurements. However, where that occurred is slightly different. So where that occurred for the ion chamber for the 80% depth dose was at 11.8 millimeters from the center on both sides, but for the gel dosimeter, it occurred at 40.1 millimeters in the negative side, sorry, and 13.6 on the positive side. And this was just taking an average of 3 pixels at a depth of 15 millimeters. The disparity was taken, was high on the negative axis, mainly because it might be slight differences in the way it was irradiated. So the phantom wasn't completely flat, it slightly bulged out a little bit, and we think that might have played a factor. The way I got the disparity is that I took the ion chamber measurements and fed it to an 8th degree Gaussian curve, and then I subtracted the difference. So if you look on the left-hand side, sorry, on the y-axis is normalized dose, and on the x-axis is distance from the center. And the same thing for disparity. Yes. And so the penumbra on the gel dosimeter is within the uncertainty of the ion chamber measurements, but the occurrence was out of uncertainty. And there are a couple of reasons why, or maybe just one reason why. One of the reasons is called the edge enhancement effect on high dose gradients. So when you've got a region of high dose, which is like, we radiate with 8 gray, and then there's no dose on the sides of the polymer gel, over time, long-lived radicals, monomers, diffuse to join the polymer gel structure. So over time, what tends to happen is that the polymerized structure will tend to grow. And since this was imaged 6 days after gel irradiation, I think it was a significant, it did cause significant changes. But to verify this, future research should measure the effect by imaging the gel at regular intervals. After that, I had a look at the normalized depth dose, or percentage depth dose. This is when the DDT anoxic gel was compared against the ion chamber measurements. So this was done at 100 centimeters source to surface distance, 3 by 3 centimeter field, and 6 megavoltage photon beam. The ion chamber reached a maximum dose of 13.8 millimeters, and the gel dosimeter reached a max dose of 3.28 millimeters. That was because there was a large initial sinusoidal peak. This was the PDD, or so normalized depth dose, was taken at a large average at the center of 9.4 millimeters due to small deviations. And these results came after I applied some median filtering. So the disparity was done by fitting an ion chamber to a curve, so 6-degree polynomial between 0 and 23 millimeters, and an exponential decay afterwards. And so there was some, as you can see in the T2 image on the left-hand side, there was some sinusoidal behavior on the edge of the ring. So this might be impacted by undersampling or truncation artifact, which is by abrupt changes in the object. So that's usually, so on the outside could be the difference between the container and the gel. And so what should be done to mitigate this is to apply a special bandpass filter to eliminate the ring effect, or reduce the truncation artifact by increasing the amount of phase code steps, or increasing the matrix size, or basically increasing your sampling size. So on the left-hand side, if you've got the graph, you've got your normalized dose on the y-axis and depth on the horizontal axis, and you can see that there's some comparison comparing those two with the initial large hump. And then below that, you got the disparity, or the difference between them. So after the initial hump, it stayed relatively below. And so with the limitations of this project, there wasn't enough analysis to perform a definitive conclusion between the DDT anoxic gels and the other gels that I've made. There's a very large variation in gel dosimetry. So even under normoxic or normal atmospheric conditions, you can have a mixture of a different, you can have a different mixture of oxygen that might have been absorbed into the gel. Even though the role of the antioxidant is to eliminate that, it doesn't completely eliminate it. And so what should be improved with this project is that we should do some more gel dosimetry metrics such as temporal stability, dose sensitivity, energy independence, dose gradient independence, and temperature dependence. And it would have been also good for future studies to do chemical analysis. antioxidant gels using electron scanning microscope. It was seen by Tetrakis and others that THPC, the really common antioxidant, reacted with the constituents, the rest of the polymer gel. And so it would have been interesting to see whether DDT did what sort of reaction that happened under the electron scanning microscope. Other limitation was that there was long shipping times for the chemicals to come. So it took around 6 or 7 months after ordering for the chemicals to come. So it left me around 3 to 4 months to try and get the gels going. Another bit is MRI, clinical MRI access. Since we don't have any research dedicated MRIs, the clinical MRIs means that it has to be shared with patients, and therefore there's a lot of time constraints onto that and a lot of time pressure. And so often you have to wait a few, like a couple of weeks or so, now a week at best, to see if you can have MRI access. And also the phantom choice. So initially, the phantom choice was not designed for MRI. It was initially designed for foodstuffs. And so I chose it because you had a airtight mechanism, really. But the problem with the airtight mechanism is that it was a metal spring. And the problem with metal springs is that you shouldn't put metal in an MRI. So this is what happens if you put metal in MRI. We've got a large hole, which is due to the metal causing the molecules in the or the other molecules in the MRI to go out of phase with each other. And when you have when all the molecules go out of phase in that particular region, you get no signal. So that's yeah. Just don't put metal in the MRI. It's just that's it. And so trying to find out what that is, I put it through CT and see that there's a spring there. So with the other phantom measurements, we just took the spring out. But really, the MRI should be so MRI phantom should be designed for MRIs, not just for foodstuffs. And so, as a conclusion, to wrap everything up, it's inconclusive if DDT is a good alternative to the conventional THPC antioxidant. And that's because there's no definitive comparisons that were made against other polymer gels, as they were spoiled before irradiation. The results of the penumbra was within the uncertainty of the ion channel measurements, and this occurred at 80% dose. Sorry, the occurrence of 80% dose was not within uncertainty. And the disparity of the normalized depth dose occurred due to the ring artifact around the container, hence that massive peak. I'd like to give a big thanks to Pejman for guiding me through the project, David for giving me the lab space and the opportunity to perform the gel, this project at Murdoch, Munir and Mashid for the Linac access and the water tank setup. I understand that using a water tank is quite cumbersome, but I really do appreciate it. John and Chris for allowing me to do my research at Royal Perth and Fiona Stanley Hospital, as well as giving generous advice on MRIs. And I'd like to give thanks to Leslie and Tegan for taking the preliminary MRIs at Charlie's. And here are all my references used in this presentation. Thank you. Any questions?
Thanks very much, Brendan. Excellent presentation. Any questions from Brendan? Great. Very clear presentation. No question. So I'm pretty sure there will be some, but to give them time to make a question. So for penumbra, if you can please bring the penumbra.
Yes.
So that's great. So you can see the comparison between ion chamber and gel.
Yes.
And we see the dose fall off. Probably, definitely can see dose fall off for ion chamber is not as sharp as gel.
No.
Do you know the reason it's not as sharp as?
It's not as sharp. Or it's maybe it's not as sharp because of the low resolution of the MR. So
that's right.
The resolution of the MR. I've actually got a slide about this actually. Let me. Nice. It's not just calibration curves, but the I thought I had a slide on this. Oh well, but basically the resolution of the MR is only 0.47 millimeters per pixel. So and because of the large uncertainty, you can say that it is accurate, but MR you know, it's not a very high resolution imaging modality to begin with. So
that's right.
Yeah.
So even ion chamber resolution probably is higher than this one because it has got volume averaging on ion chamber. That's great. My sheet has got a question.
Go ahead.
Thanks, Brendan. That was a really nice presentation. I hadn't seen one like this for a long time since we went online, because yours felt like a real face-to-face one. So I do appreciate that.
Oh, cheers.
So what's the way forward now?
Well, the way forward now is to see if we can apply this gel to patient specific phantoms or filling phantoms with gel, but that's in the far future, and hopefully we can establish a gel lab here in Charlie's. But before we get to the stage of using phantoms, we need to do more testing to see whether this gel is a good substitute. Sorry, let me rephrase that. Whether the antioxidant used in this gel is a good alternative to what's conventionally used. So the main drawback with these gels is that they're very finicky and they're very hard to make, and they're also quite toxic. So if we can reduce the toxicity, it can be something more attractive and something more applicable to what can be used in the clinic. So that's the way forward.
Okay, lovely. Thank you.
Excellent. Any other questions? No, all good. Cool. No questions. Brilliant. So I'll stop.